Last lesson, we were looking at something called mathematical induction. And like I said, usually we don't really care, well, I shouldn't say we don't really care, but proofs are like a little add-on, right? That we just say, hey, this is actually something that we can prove, right? But like I said, this topic, the topic, mathematical induction, is essentially the skill of proving something. And I said that that was really important because some things can't be, I guess, proven just by some theory, right? As in, like, you think about a scientific experiment, there's no theorem that just gives you the answer. You have to do experiments to work out if they're true. And this is kind of true of induction as well. We're kind of running these experiments, right? Like, for example, calculate these for me. What numbers do we get? 4? 4? 24, 24. Okay, what do we notice about all these numbers? 4. They all have a 4. What's a kind of theorem that we could hypothesize? 4. 4 is the hypothesis, is that right?
Take 5. 5 equals 4.
Equals to 4. It always equals to 4. Like, this next number, what do we expect it to be?
4.
624? No, is it?
I think the theorem should be 4 equals to 1. Is that actually? Harry doesn't know, he used to calculate. No, I did.
Can you just calculate for me? Callum?
Yeah, that's right.
Yeah, alright, sweet.
Smart boy.
So, what's the theorem here? What's the hypothesis, you think?
The last numbers are 4.
The last numbers are 4? The last time we were thinking about a particular pattern, this type of induction, although it's a similar skill, we're actually looking at divisibility. If all of these end in 4, right? If all of these end in 4, I'm hypothesizing, hey, maybe they're all divisible. Are these divisible by 4, do you reckon? Not too sure. That's something to test. What about these? Can you test these out for me? Are these all divisible by 4?
Yeah, that's what I said.
Yeah? Is that what you said, Harry? Yeah. Okay, good. Yeah.
No, I said square root.
Square root, okay, cool. Sorry, how is that question phrased generally? It's phrased like this, right? Remember, induction questions, proving, yeah? So e.g., this is the first one, write this down with me. I actually remember someone last year when I did this, that the hypothesis, they were like, oh, they were just like, oh, anytime it's ending in 4, it's divisible by 4. And then we thought of some pretty easy counter examples, like, yeah, wait, what? 32. Oh, yeah, right. Or any number that ends in 4 is divisible by 4, but yeah, obviously yeah, 34, right, exactly, yeah. So, yeah, it's not always immediately obvious. Matt's question, yeah, would they ever give you one to work out the rule like I did in the first lesson? Like, I don't know. I haven't seen that before in HSC, but I guess there's no reason why they couldn't ask you that. Generally, though, the questions will be like this, right? And like I said, it's the same kind of skill, right? Because, like, what's the problem with doing this? The problem with just doing this is that we have these individual dominoes, and I can't just say, oh, I reckon it's true for all of them because we've done like 4 examples. Like, you always just want to say, let's just do one more, and yeah, if it's one more, then it works out, right? But that's why we go through this process of induction to work out whether it's true or not, right? So we had 3 steps. What was that acronym I gave you? Tap, right, dominoes, we're tapping him over, yeah?
I didn't even know you.
Tell them what you're going to tell.
All right, so tap. What's the first step, Joel?
Yeah, test 1.
So step
Sometimes it might not be 1.
1? Yes, good. Yeah, so
I'll tell you.
the first couple of ones are pretty nice, and they do tend to do 1 a lot, but you just be aware they can do different ones, yeah? So test true for n equals to 1. So that's basically saying, like, okay, does this thing actually work, yeah? So 5 to the 1 minus 1 is equal to 4, which we've kind of tested already there, which is divisible by 4. Therefore, it's true. Okay. Step 2, Harry, what was that again? Assume.
It's true for n equals to k.
Yeah, that's exactly right.
Why can't it be n equals to like c?
You can use C if you want.
Okay.
Now here's the thing, right? Like, remember in the other induction questions when we were looking at, yeah, adding all of these up is equal to something, right? We were actually given 2 sides for the induction, right? But this one, it's just saying, show or prove that this is divisible by 4. There's no, like, other side. So, I mean, what are we actually trying to prove? Like, we're assuming this is true, but like what are we assuming then? K on 4, you reckon? Like,
Well, that whole thing on 4.
like that kind of? Sorry?
Oh, that means like 5.
So Laura has a question for why are we changing n to k? Like what's the kind of difference? There's some sense that it's like a convention, right? But essentially, this is in a general sense. When we say 5 to the n minus 1, I'm saying it works for any number, right? But when I choose k over here, I'm kind of picking a specific number in some sense, right? But the reason why we leave it as k is because we don't want to go to this trap of like choosing individual ones. Like k leaves it general, but it's also specific. That's kind of contradictory, but that's the idea behind it, yeah. You're right. Over here though, like what goes on the other side?
4.
Just 4? What's another way to express these kind of numbers, right? Like this is a 4, this is a 24. But how do we know that they're divisible by 4?
We just know.
Because if you divide them by 4, then
Yep.
you will a number without decimal.
If you divide them by 4, it gives you another number without a decimal, or another way to say that is you can write this as 4 times some other number, yeah?
It switches between 124.
So over here, what we can say is, all right, if I can multiply it by some other kind of number, right? Sorry? B, yeah, you can use B. What they tend to use, you can use B. They tend to use like M a lot, right? It doesn't really matter. M's good, where M is integer. Doesn't really matter, but hey.
Yeah, why do you use the same letters? Why can't you use like a J or something?
You can use whatever letters you want. There's just convention, really. These don't matter at this point, yeah?
M is greater.
You're agreeing. Yeah, it's true. No, it's also.
It's also meters.
Capital M. We don't usually. That's like mega liters or something. I don't know.
T's annoying.
Yeah,
T's
T's
like,
not
Oh, T is the worst.
Yeah, T is not
also
good.
like period.
T or X.
So I thought I had like a little squiggle on.
I wasn't expecting to get a massive discussion about which letter to choose. Okay.
You could agree with this, sir. T is horrible.
M is also like great.
Yeah. So
Yeah, we're-
it's all about
Look at
context.
this and think gradient, dude.
I do.
I think meters, that's 4 meters. I'm sorry.
I mean,
I think it's 4 million.
All right. Last step. Step 3. What's the last step?
and
Prove. Kyle, what are we proving? Next one. Okay, so again, just kind of giving you some meaning behind like what are these 3 steps and why they're so important, right? Testing is true for some specific one. That's important for us to get the ball rolling, yeah? And then assuming true for n equals to k, we're saying, okay, I don't want to go through this whole process of just like proving it for every single one of these. So I choose k as some term over here. We're just assuming it's true. But if we can prove it's true for n equals to k plus 1, we essentially do this for all of them, right? Because we can just like keep moving these along now. Like once you do it for 1, then you can use this for 2 and 3, and this k plus 1 thing just goes on forever. Yeah.
should we say that n is a integer?
N is an integer. Yep.
Should you specify that at the beginning?
Sorry, yeah, it should say over here for n integer. There we go. It does say that. Sorry, I was a bit lazy there. So n greater than or equal to 1 integer. Yeah. Good point. That's very important. And I guess, yeah, and I guess you're saying that k is an integer too, like whatever, right? Yeah. This one over here though, this changes now. We get 5 to the k plus 1 minus 1. What's that going to be equal to?
Oh, you 4m.
4m? We like that?
Oh, I know what you mean.
There's nothing actually inherently wrong with that. It's more of a pedantic thing, to be honest. Like,
4p.
yeah. So this is the thing, right?
Fine, it's the same one.
Yeah. If you leave it as the same one, strictly speaking, what you're saying is that m is just like a specific number. So you're kind of saying that 5 to the k minus 1 will be the same as 5 to the k plus 1 minus 1. Like that obviously not true because like when you multiply these ones, you're multiplying by a different number. So just as a convention thing, we change the second one because these two obviously can't be the same. I think they use n in your example, so just go with n. Again, the letter you choose is kind of arbitrary, right? As long as you define, it's a cap. Yeah, it's a cap. As long as you define what you're using, yeah, that's fine. But can you see why these two can't be the same, right? Because they're ones after each other, so we can't really, get the same. The other thing, though, and again, I guess this is a convention thing, but writing this as a statement, we can't do either because we haven't actually proven this. We have to prove it. So you remember last lesson I wrote RTP? That just says I'm required to prove this. I haven't actually proved this yet, but I'm writing this statement as this is what I need to do. If you forget to write it, I'd be surprised if they would mark you down. But like I said, like they can often determine marks based on like neatness and stuff like that. Like so, yeah, potentially, right? Like there's nothing mathematically. You haven't made a mathematical error. It's more like a convention thing. It's like a grammatical error if you want to think about it. So this is something I've heard, right? Like when they're determining if like two people are equal or something like that, then if they literally have nothing else to compare on, like you've got all the correct answers, you've got all of that stuff, then neatness can be one way to determine that. But you've got to think about it, right? Like think about how many people are sitting this exam in the state. There's like what 5,000-10,000 of you, right? If 10 people get the same mark, like how are they going to differentiate, right? Essentially, right, here's the problem with this induction proof, right? We want to work with the left-hand side, but it doesn't look like there's much we can do with this left-hand side, yeah? Harry, what is the first step you take? What did you do?
Why are you asking me?
Because I think it's very interesting what you did.
I did it as a joke, but it can't. Well, we've got our left-hand side on the left-hand side. And so we just plus 1 to both sides.
Okay, so that's actually something you do if you want to, right? You could plus 1 to both sides. At the end of the day, what you want to think is how can I get to what I need to get to? And what we need 4 times n. And I guess the first question you had is like, where does n come from? N's not even here, right? Just disregard that for now. Like 4n can be anything. It could be like 4 times something. So as long as I can sort of incorporate a 4 into there, I'm on my way to solving this, right? Or proving this. So initially, it doesn't seem like there's anything you can do with this, apart from doing what Harry did. This part of my expression that I can do something with. Like there's something I can do. I can rewrite this in a different way, which is helpful. Because you remember from the previous induction question we did, we had to use step 2. Right? We had to use step 2 for something. So essentially what you want to think about is how do I get step 2 into step 3 somehow? That's basically what you want to be thinking, right? When I'm looking at this, is there anything I can do with this? 5 to the k plus 1. That's what I want to be thinking about. Is there another way I could rewrite it potentially? Yeah? Have a think. Like what does 5
in brackets and then to the power of 1.
5 to the power of k in brackets? Like that? And then what?
And then 1.
Like this? Are these the same? Are these the same? Think about, so that, yeah, I like your thinking. You're thinking about index laws, right? What's another index law which involves addition rather than multiplication? So Harry, 5 to the k times 5 to the power. Yeah, that's exactly what it is, right? Yeah, because remember, so I'm doing dots for multiplication. Yeah. 5 to the power. Is it okay if I write dots for multiplying? Yeah. Okay. So. Yeah. So this here over here, right, is just 5 to the k times 5 to the 1, and that's the same because we have the same base. So remember, we'll go back to my original question. My original question was, hey, can we find this here anywhere? Yeah. And now we're starting to see it because there's a 5 to the k here and there's a 5 to the k here. But this kind of annoying -1 thing though. Check on the outside, you reckon? On the other side, yeah. Yeah, exactly. This one over here, that's when the rearranging is helpful. There's no reason why I can't rearrange this thing, right? Because this is an equation, essentially, right? So what you can do is you can rewrite this. Do my rubby thing. All right, I'll rewrite it up here. You can rewrite this as 4m plus 1, yeah? That's all fine, right? Nothing wrong with that. All I've done is add 1 to both sides. And then you go back to over here and you're like, well, now I can make a substitution pretty easily. I can just say that that's 4m plus 1 times 5 minus 1. I mean, let's put the 5 out here for consistency. Again, like, don't forget what your goal is. Your goal is to say, hey, I want to try and get 4 times something. That's what I'm trying to do. That's what I'm trying to prove. Write that down and we'll see how we can finish it off. Callum, what did you do next? Expanded. Never a bad, never usually a bad thing to try that.
Oh,
Yeah.
So 20m plus 5 minus 1 is okay, cool. And then we've got, I'm going back over here, 20m plus 4. Again, right, like what's the point of this? Like what are we trying to do? Never lose sight of that. We're trying to show that this is equal to 4 times something, right? So where do I get 4 times something from this?
Divide that by 4.
Dividing by 4, and go back to Joel's answer of like what is something that's divisible by 4, right? If you divide it by 4, you can or you can opposite way, you can multiply it by 4 and some other thing, right? So where's 4 in these guys here? Yeah, 20. Yeah, how many times is 4 going to 20? 5 times? How many times is 4 going to do this? Just once, right? So essentially, when you say divide, another thing we can do is rather than dividing, because we can't change the expression, but to show, for example, like 24 is divisible by 4, you can write it as 4 times 6, right? You can write it as its factors. So this guy, you could write it as its factors. That's the process of factorizing, right? So we take out the 4 there, and you get left with 5m plus 1. Just to wrap it up nice and neatly, yeah? If you remember, when we introduced m is an integer already, right? So if you ever do 5 times some number and add 1 to it, that's actually still always going to be another integer, right? There's no way you can get a decimal out of that, right? So just to make it clear, we can say where 5m, yeah, or 5 plus m plus 1 is integer, and then you can just say that that's for n, which is what we're trying to do back over here, right? Which is the
It's pretty sketchy.
Yep. Questions about that?
Yes.
Yeah, James.
I don't know. It doesn't feel like very logical right now.
Where? Which bit?
So it's literally just saying that, oh, you get this thing and then you get integer. And the other one equals
You're just saying that,
the same, right?
you're just saying that they're both equal integers.
That's like my retarded.
So let's go back to this, right? Are you okay with this statement here, right? If you can prove that this is equal to this, then we've proven it true for all the numbers, right? Are you okay? Are you on board with this guy? Yeah? So as long as we start with this side, and I can end up with this side, then that's all well and good. Yeah? I guess the question remains is like, what is n? And n is just like some other number. So the goal is to rewrite this as 4 times something, yeah? Yeah. Yeah, so this thing, yeah, we're 5, yeah, so we get up to this point, and we're saying like, okay, I will need 4 times something. How do I get 4 times something over here? That's essentially what you're doing here. You're doing 4 times this whole thing. And hang on, this whole thing, that's just an integer, right? Because it's 5m plus 1, which is always going to be an integer. So just the last, how do you finish up your English essays?
By the process of mathematical induction, it is true for any conclusions. By the power invested in
Sometimes they'll abbreviate this. They can say it's like PMI. Yeah, PMI, process of mathematical induction. Yeah. So, 3 steps, right? Test, assume, proof, and that's induction in a nutshell for divisibility.